Now we'll stir. It comes. We are noticing a hissing sound coming from the baking powder.
Close to concluding today's subject, solubility. And now the last part will be comparing different substances in their solubility in one solid, in this case the universal, in one solvent, in this case water. So we have baking powder. It is sodium bicarbonate, sodium hydrogen carbonate, and also sodium chloride. Both made for human consumption. We bought them from the stores. They have to be dissolved when we make use of them at home. When we use as a source of carbon dioxide, it has to be dissolved. Sodium chloride has to be dissolved to be part of the food we eat. We shall have some good idea about their solubility in water. And we have already seen how soluble ground sugar is in water. So we'll take same volume of water, these two beakers, same mass of these two solvents, namely sodium chloride and baking powder, and we're going to stir this for 2 minutes as we did previously with this one, and then we'll leave it for some time and then compare their solubilities. So ready to give it a start?
Okay, so add table salt. This is going to be solute for this experiment to have a standardized amount. I will take 2 tablespoons. So I'll add equal amount of water to prepare. That's about enough, I think. So we'll have for this, for the baking powder. Here I have sodium bicarbonate, also known as baking powder. I'm going to take 2 tablespoons. So we'll add the same amount of water that we did for the sodium chloride or the table salt. Okay, that's enough. Now we'll stir. It comes. We are noticing a hissing sound coming from the baking powder. As you can see, there's sound and bubbling coming from the sodium bicarbonate, the baking powder. I think it's because baking powder is more reactive than the table salt. Okay. So
Is that so?
why is it when we look at it, I think it's because it's producing the gas, the carbon dioxide gas. That's why it's making it. But in the case of sodium chloride, it's just a physical change, meaning we're just dissolving it. But here, I think a chemical change is taking place, meaning that there's an emission of a gas, carbon dioxide. That's what we see over here. So we're going to stir our compounds and we're going to see which one dissolves faster and if there's any difference in the solubility. So you can stir with your spatulas like this. Okay, the sodium chloride or the table salt seems to have fully dissolved. I don't see any remaining sodium chloride. Mine has completely transferred the water too. Okay. So let's compare it. We have the baking powder here, or the sodium bicarbonate. We have the table salt, or the sodium chloride. Then we have the grounded sugar, the experiment they carried out earlier. So we can still see a bit of the sugar left undissolved. Yes. Okay, let's see the table salt. Okay, do you see any suspensions left?
No.
Okay, yeah, it's almost completely dissolved. How about yours? Well, we can't see it because the water has been changed by the baking powder, but I think it has dissolved.
Yes.
Yes, so now as you can see, we have the equal number of volume of water. We have added equal solvent and we have stirred all of them, so that can't be the factor affecting them. So what do you think is affecting the solubility? Some residues left here, the others have completely dissolved. So what factor do you think is playing a role here?
I think it's because water is a good solvent.
Okay, that's right. I also think that apart from the water being a universal solvent, the nature of the product that we're dissolving in the solvent has, a factor to play. The sugar has not completely dissolved and the salt has completely dissolved. That means the character of the salt, it's more soluble in water than the sugar. I think that's what took place over here.
I have a question for you. What is the force in action in making the solids soluble in the given soluble total K? In the case of sugar, the case of sodium chloride, and baking powder.
How do you mean?
What do I mean? Okay. The sugar, when it was powder, the sugar molecules interacted with each other. What were the forces that kept them together in the solid form?
Well, since sugar, it's not like a compound. It's a compound. So I think the random dispersion forces may have kept it together.
That's one. You always get random dispersion forces in any substance. But what other non-covalent associations do you think play a role here? Sugar, sucrose, is a disaccharide. Glucose and fructose. There are many OX. The OX would associate with the surrounding water, in this case the solvent, through hydrogen bonding. So that is what is keeping it in solution How about in sodium chloride? Where does it dissolve?
It's an ionic form. It's an ionic compound. So it's a crystal. It's in a crystal form. So the forces that keep it together, when it's put under water, it forms ions, mobile ions. So in the solution, we'll have sodium positive ion or cation and chlorine minus ion or an anion in the solution.
So what kept the sodium ions closer to the chloride ions, ionic association, were replaced by dipole associations between the ion and water molecules. In the case of sodium, it would be surrounded by water molecules through the oxygen ends, of the chloride through the hydrogen ends. So here, one form of association is being replaced by another. The one that gives more stability dominates, because the solid is dissolving in water, then the associations we see in the solvent are stronger than the ones we have when it was the solid. How about in sodium bicarbonate?
It's the same. I think it's the same as sodium chloride.
Because they are ionic. But as you rightly said, read it, we saw gas coming out, effervescence. The carbon dioxide is a product, so it was a chemical reaction, not mere dissolution. So to wind up what we did today, we have seen the factors like the surface area, agitation or steaming, temperature, and nature of the substance affecting solubility of the substance in a given solvent. What was common in all experiments today was the solvent. The solvent did not change. Had we replaced water with hexane, would we see similar solubilities?
No, probably not. Because water is a polar solvent, so it will dissolve polar compounds. And the hexane is non-polar, so it's a non-polar solvent. Like dissolves like, so non-polar compounds would be most likely to dissolve by hexane.
Thank you very much. We shall see you next time. With the last part of the experiment, what was done was to make this solution out of baking powder. It still looks cloudy. It has not settled down. We don't know if everything has dissolved or not yet. It's going to take time, but I would like to filter it out to see if it can give us some idea about the amount of the substance that has dissolved. If we see some precipitate on the filter paper, then that indicates it has not dissolved completely. We could do the same thing with this one, but this is with sodium chloride. It seems more clearer, even though there is some like this one. It's not as severe as this one. So by filtering, we can see if really everything has dissolved or not. To conclude today's experiment, what we have been trying to do is to see if solid solids dissolve in the most important solvent, water. Water is considered to be the universal solvent. Of course, here we have to be careful not to think that it dissolves everything. That's not true. There are substances that do not dissolve in water. But there is no other solvent other than water that dissolves as many solids as possible. The solids that dissolve in water are either polar or ionic. Those that are non-polar do not dissolve in water, but still it makes it number one as a solvent. This is very essential because in everyday life activity we dissolve substances to make food items, beverages that we drink like lemonade. It could be alcoholic beverages like tella, edge, beer, wine, liquors, or Coca-Cola, Fanta. If things do not dissolve in water, they don't become useful. So it is important to know how we can dissolve one substance in water by either increasing the temperature or by stirring or by grinding, which is a means of increasing the surface area, which increases the contact between the solvent and the solid. So through today's experiment, we have been able to see and demonstrate that these factors affect rates of dissolution. On the side, we've seen two colorless solutions of silver nitrate and sodium chloride. When mixed, made a white precipitate. That is not a simple physical process, it's a chemical reaction. When we also dissolved sodium bicarbonate in water, it was different from the others. In a way, it produced gas. The gas was carbon dioxide. We also took metallic sodium out of the kerosene. It's a very soft metal. It has unusual properties, unusual from the properties we know so far about metals. When we dropped it into water, it reacted vigorously, producing hydrogen. We could have checked what that gas was, but we're going to see that in the next lesson. In the next lesson, we will generate gases and detect what gas they are from the known properties they show, either their physical or chemical properties. That's all for today.